So today we're going to start chapter 8 of this book, Functional Programming Made Easier. You can get it at leadpub.com, fp-made easier. And we're going to talk about abstract algebra today. So I know some of the words that are here, but I certainly don't know all of them. So I feel like we're going to learn some stuff today, which is cool. Hey James, how's it going? Man, you got that greater than 12 symbol and everything. 18 months. My goodness. Thank you so much, James. Appreciate it. All right, many concepts from mathematics that functional programming borrows heavily from. One of those areas is category theory. We'll see that once we get to functors, applicative, and monads. Another area is abstract algebra. Take a cursory look at these concepts as a whole, since we only need to understand how it relates to programming. The concepts are very simple enough that you can, that you could have easily learned concepts in your algebra class. Okay, too abstract to teach most students that won't need them moving forward. Still set up to produce industrial revolution workers. Okay, that's a very specific statement. I like it. But we live in the information age where the concepts are beneficial to us programmers, and so it's worth learning. Yeah, I mean, like, learning programming and math is pretty pervasive now. I'm actually surprised that STEM doesn't contain, well, I guess it contains technology, right? So I guess that's close enough. Another thing to keep in mind is that these concepts weren't developed by one person over a short period of time. Many people, different countries, different areas of mathematics. Cool. The names of similar concepts are so different from one another. For example, monoid and semigroup are two concepts that differ by a single rule, and yet their names would suggest that they are very different ideas. That's an interesting point I wouldn't have thought of. Like, I just kind of took it at face value that they were called semigroup and monoid, but I suppose they are pretty different terms. Anyway, that's kind of interesting. Yeah. I think this is like a really common thing that people like don't realize is that these concepts aren't really that complicated. They just have names, and if you understand the names, it can help you sometimes. Sometimes it doesn't help you, but like knowing the rules is pretty helpful, or knowing how things behave. Hey, Sky Bro. So as a quick review, let's look at some binary operators. Binary means two. Two stands for two parameters. The operator is a symbol that implies a very specific function. Yeah, that's pretty basic binary operator right there. Yep, there's a bunch of binary operators. Cool. Usually written in fixed. A binary operator dot is, I suppose I could call that C dot. I escaped evil. Okay. Explain. I feel like I should know, but I don't know what that means. Okay. I see. So an associative binary operator is true if you can switch the order of the operation. So if we take A after B and C, should be the same as A and Z, and then Z after. Okay. You can remember what this means if you consider the parentheses as the mechanism which associates the operator with its parameters. Here we're using C dot to represent any binary operator. Yep. Yeah. Whenever it's associative, we can arrange them. Yep. Okay, cool. And we're equally familiar with non-associative operators, division and subtraction, where the order does matter. Cool. Commutative. CXC. Vimini Max jokes never get old. Um, Binary operator C dot is commutative if the following is true. A after B is the same as B after A. I'm just gonna use after because it's like I know that this is not composition, but it's easier to say out loud. Or I guess you could just say and. I don't know. We've seen plenty of examples of commutative operators. Yep, and non-commutative operators. Closure. In programming, the term closure has a very different meaning than it does in mathematics. Let's investigate mathematical definition. Take the following set, true and false. We'll apply the binary operator and to every combination of the elements in the set. Notice how the result is always a value that's in our set. When this is the case, we say the set is closed under the operation of and. Take another set, 1, 2, and 3. Is this set closed under binary operator plus? No, it's not, because 3 plus 3 equals 6, which is not in the set. Cool. I think none of the the traditional mathematical operators would be closed under the set 1, 2, 3. If we consider the set of positive integers, should be closed under plus. It wouldn't be closed under subtraction. Did you know in Sweden we officially pronounce F? Here, I'll bring up an example. This F, like A, B, as A ball B. Interesting. That's kind of a funny name. So I call this C dot probably most often, or just dot, because that's what it is in LaTeX. I don't know how you make it red offhand, but anyway. Yeah, so division and subtraction definitely not closed, but it's closed under multiplication because multiplying any two positive integers is a positive integer. All right, magma. Magma is a red hot liquid rock. True. But it's also an abstract algebra structure. It's sort of the bedrock of everything we'll talk about here. All other algebraic structures we investigate will build on this. Magma is a set that's closed under a binary operator. I actually didn't realize that the yeah, I understood. I understood where you're going with that. I didn't realize that it's a set is a set that's closed under a binary operator. I thought the magma was the binary operator itself. Like any binary operator is a magma. Is a set that's closed under a binary operator. Okay, let's look at some examples because, you know, I'm an examples guy. I've explained that many a time. So if we have the set M, set of all booleans, and the binary operator C dot is logical and, here is an example of not a magma. So the all non-negative numbers and subtraction. We saw earlier how subtraction is not closed over the set of positive integers. This is also true for the natural numbers, which include 0. Here's the formal definition of a magma using mathematical notation. So for all A and B in some set M, AC dot B must be in N, M. Or I guess this is in, well, A and B in set M. Using the operator must also be in M. Okay. Yeah, for all A and B that is an element of M, it follows that. This is the one you just don't say out loud. The result of A dot C dot B is an element of M. Cool. Semigroup. Any questions so far from anyone? Like, I feel like this has been pretty basic so far. It's kind of interesting the definition of magma. Okay, so a semigroup is a set that's closed under an associative binary operator. So okay, so the operator is the thing that's defined, or sort of that defines the thing, and then it is a semigroup when this set is closed under that binary operator. Okay, cool. I'm starting to understand, or like that makes a lot more sense now, right? Because like the set of all strings is closed under this, which makes it a semigroup operator. Or sorry, a semigroup magma. Magma. Non-empty strings. Okay. Does that matter? Why does it have to be the set of non-empty strings? Wouldn't the empty string just add one more thing to it? I just find it odd that this is capitalized. That's why I'm curious. I don't think it matters because it's also a monoid. So, anyway. It's defined in terms of magma. Uh, could you explain what you mean? I'm not sure I understand the question. If it is. Okay, so we can easily justify that it is when we see the above. The order in appending strings doesn't matter. We can first append AB with CD and then EF. Or we could first append CD with EF and then prepend that to AB, or append that. Fine. So magma defines the empty value. Magma defines the empty value. Sorry, still not following. So the magma is a set that's closed under a binary operator. So this is the set and this is the binary operator, and my point is that I don't think it matters whether S is a set of non-empty strings or the set of all strings. That's okay. I'm legit trying to understand this as well. Like make sure I understand, because I actually misunderstood what the term magma meant from the Wikipedia article. Although maybe this is like not entirely correct, but it does make sense to me. So like there is also a magma for the set of non-empty strings that is the monoid, right? And the binary operator. Oh, no, that's not a binary operator. So that's not even a magma. A monoid is a completely different thing. Anyway, yeah, it's we're still learning. So we got to get to monoid to see if this matters. But my feeling is that it doesn't matter. But maybe there's something here that we don't, that will explain this further. Here we go. Yeah, here's an example of not a semigroup. So natural numbers with the operator minus isn't closed, therefore not a magma. Okay. So the formal definition of semigroup using some mathematical notation. So for all A, B, and C in set S, it what do they call this? It something. It follows that the associative property is true. Mm-hmm. Yep. All right. So the semigroup type class is this, and we can see our binary operator there. And some common instances of semigroup are string, list, and array. Great. All right, monoid. If we add one more requirement to semigroup, we get a monoid. Okay, so it's a monoid is a magma with additional properties. All right, so given E in M for all A in M, okay, so these are both elements of the set. A dot E is the same as E dot A is the same as A. Okay, cool. The neutral element or the empty element or identity can be applied to any element of the set, including itself, to an element of the set and have no impact on that element. Here's an example to drive home the point. Yep, here's the set of all strings. And the append operator. All right. So, yep, here's another monoid for addition. So this is the magma, and then this is the additional property. Yep, so it's a magma. It's a semigroup because it obeys the associative property. Then it's also a monoid because it obeys the identity law. Okay, so another example. M is closed under the operator. It's a semigroup because it's associative and it has a natural empty element. False. Neat. Okay, so 0 and 1 and multiply. Yep, that makes sense as well. And the monoid type class. Okay. So semigroup is a superclass of monoid, which says that every monoid must first be a semigroup. Then we add an empty element. Empty. Yeah, this always trips me up, the reverse fat arrow. But actually, does it matter? It does. So the good news is you can't do it the wrong way. So that's pretty helpful. Because in Haskell, the syntax is flipped. All right, so here's the string instance. Here are the string instances. Minor typo, but I suppose I should write it down. I'm just keeping like a Google Doc of these, by the way. 301. So here is a foreign import to let PureScript compiler know how to call a JavaScript function. The semigroup instance calls JavaScript, presumably for speed, to append the two strings. The empty element is the empty string. Okay. I've never used the foreign import system in PureScript, but I think it's discussed later in the book, so that'll be useful. I've never done any like FFI stuff, so. All right, so when programming in a statically typed language like PureScript and Haskell, we concern ourselves with types, not sets. How do we bridge the gap between mathematics and programming? A monoid is a set with a binary operator. A monoid is a type with a binary operator. Earlier, we talked about types having inhabitants. We can think of types as sets of inhabitants. So monoids in math are isomorphic to monoids in programming. Set in math is the set of inhabitants of a type in programming. Do we really need to have this like distinction? Like, how much does this actually matter in practice? Like, I understand that they're isomorphic, I guess, but does the distinction really matter? Isn't the set of inhabitants of a type just a set? Maybe I don't understand. Or maybe I'm missing some like fundamental thing. Anyway, if somebody has any idea, feel free to let me know. Okay, so let's say we want to write a function to combine a list of monoids. So combine list of monoids. Um, we start with mempty, and then we start adding x's until we find the end of the list. Okay, A is a constrained to be a monoid. Oh, wait. Sorry, we're building an accumulator basically from x's. My bad. Combined list of monoids is point free. Um, okay. By the way, this is just a fold. So I don't think we've talked about folds yet, but you could literally just fold like, here, let me just write it down. So if we wanted to do, I'm just going to call it combine for all A, monoid A, list A. Actually, there's probably even there's actually probably already a function for this, but I guess you could do something like fold R mempty, and I think that would compile. Oh, right. We need to uh, isn't that what it is? Where's list come from? Is the type not defined in here? I'm very confused. There it is. Re-exports from data list types. Okay, so we need lists, and we're also going to need folder probably. Fold. Yeah, so anyway, folder. But why is this not showing? Spago build. Okay, it's better now. I'm not sure why I was complaining. Anyway, you could rewrite this as this, which is probably a little more right term. Idiomatic. There we go. Okay, so notice that we start with mempty. Yeah, we already talked about that. We could not do this with just a semigroup constraint since semigroups don't have the empty element. But what if we wanted to write a version where we could also allow semigroups? We could start with first element instead of the empty element, but there'd be no first element in the list if the list is empty. We need to guarantee that the list isn't empty, and we can do this by using the non-empty type. Okay. So import data non-empty. That's interesting. So this one is just, I guess you would just use fold map. There's already like, is there just a fold? Yeah. So this is just fold. Pretty sure. So we have a foldable of M. Oh, right, because it we don't have an empty, but this is special because we have this. So maybe there's something in non-empty that does this. So data list non-empty. There might be a fold in here which only requires semigroup. That's interesting that it still does this, even though you don't need this. How is this implemented? Yeah, that's kind of funny. I wasn't expecting that, but like it makes sense that it would be that. So this needs to be. Oh, but not here. Oh, but fold map also wants this. which is weird. Why does it need that? How is fold map implemented? Ah, because it's overfoldable. So it's not specific to non-empty, which is the problem. Okay, never mind. You can't just use that. We also can't use fold R. So you would have to implement this in a different way. It's fine. I'm not too worried about it. All right. An empty list. So oh wait, yeah. So we actually can do it. Sorry. I'm being stupid. Sorry, silly. All right, so we have a non-empty list, so you can just write non-empty x excess. And because we can pull this off, you can just use fold R x excess. I'm pretty sure. Yeah. Okay. There we go. Ay. I know what I'm doing. I swear. Can you use the operator here? Maybe because it's unknown. And then also this is complaining because it doesn't need this. Okay, cool. So that's pretty neat. This would be pretty verbose to look at, so it makes sense why single letters were used. Not clear why F was used. Yeah, so this is just functor, which we'll talk about later. We're used to seeing A, but why F and A instead of A and B, for example? Turns out that all collections of elements, at least every collection I can think of, are also functors. We haven't learned about functors yet, but clearly the author of this type understands functors, and so F is used to represent functor. Here's our type signature for combined non-empty list of semigroups. Notice how we specified the F as list. That's the collection or functor type. The second type parameter is A, which is the element type. This could be defined for any foldable, I suppose. Any non-empty foldable. Let's look at, is there like a concept of a non-empty foldable thing? Not sure. Let's look at the constructor for non-empty, which is also called non-empty. We have this A and FA. So yeah, I think you can, because you could just say for all FA foldable F semigroup A F. This should still compile. And same thing is true here. You could say F foldable F monoid A and then F. So those are even more generic, which is nice. So that works under any foldable thing. It's interesting to me that it can even use the fold R though. If I want to see how this, I think that this is probably just implemented in terms of the most general thing possible. Yeah, because it comes straight from foldable. So we just implement an instance for foldable of list, and then you're good to go. But this is just a re-export, so you don't even need this. You could delete this completely and then import class foldable and folder, I guess. Nice. You do need non-empty, which means you still need lists, but anyway. Okay. There's a helper function to convert a non-empty list to a list, to list. Remember that this tilde arrow is a natural transformation from one functor to another. Yeah, this was really cool when we saw it before. Functors are coming, I promise. It's shorthand for this. You may be wondering how you go from list to non-empty. There's a helper function in the library for this. So from empty list? Why would we call it from empty list? What? Wouldn't we call this to non-empty list? I'm a little confused. So if we go back up here to non-empty and we look for, yeah, from list. Sorry, not to non-empty. Usually it's from list. So anyway, this is a weird name, but you get the idea. You have to return maybe because if it's empty, it can fail. Okay, so groups. If we add one more requirement to monoid, we get a group. A group is a monoid where every element of the set has a unique inverse. Here's the formal definition of a group using mathematical notation. All right, let's see if we can read this. So for all A in G and A prime in G and E in G. Oh, okay. Yeah. What's another term for this? Like, no, I guess this is just group. I'm thinking of something else. Cool. This is pretty sweet. So, where every element of the set has a unique inverse. So essentially, A prime is the unique inverse of A, and E is the empty element. In other words, the identity element. Let's see how this works by starting with the following monoid. We have the natural numbers under plus with the empty element 0, or the sum monoid. Let's add the group requirement. Okay. Notice that the empty element E is its own inverse, and it's unique since it's not an inverse for any other element in the set. If we take E and apply to E, we get E. So it acts as identity element to all elements, but also as an inverse for itself. I feel like this was worded a little strangely, but I'm going to read it again. Yeah, yep. Pretty much. Yep. Okay, note that inverses A prime, inverses, take any element, and when applied with the binary operator, map them to the identity element. Yeah, I feel like this could be worded, this sentence in particular could be worded a little bit better, but like I guess it's fine. I understand like what they're saying at, right? Like 1 and -1 are clearly each other's inverses. I also can see how it's really difficult to encode a group in like programming language. Are there programming languages that work well with groups? There must be. But I could see how it would be hard to define a group for uh all integers. Like cuz you basically need in this case you could use a function that defines how to get its inverse, right? I have no idea. But like in this particular set, you could have a type class that defines how to get the inverse, right? Cuz by just negating it. Um but yeah, maybe. Maybe. We might be diving down the programming language compiler theory stuff. So, okay. Here's another example of a group. So we got multiplication and e equals 1. So, what is this group? Sorry, what is this? I'm not sure what this is exactly. So, oh, I see. 2 times 1/2 is 1. Okay, sorry. I now see it. It's like 1 over n each time. Um, I don't work with groups very often. Well, I haven't in a long time, I suppose. And I guess I didn't really think of them that carefully as groups. Maybe I should have. Here's an example that's not a group. Uh, yeah, because again, it's actually this is kind of a weird example. Oh wait, no, this is um a magma because it's closed, but it's not a semi group. Is it a semi group? Um, sorry, I'm blanking. What? So semi group is associative, right? Yeah. So no, it's not. It's not even a semi group. So it can't be a group. Yeah. So okay. So it provides a function g. It converts a g to another g. G inverse returns the inverse of the value it's given. Right. So, what? What am I doing wrong here? Probably thinking it's Haskell. Okay. Wait, did I just delete my... Oh, I see. So negate requires a ring. Um, deriving. Can I just do deriving new type? Or is it derive? Semi group? Oh, we probably can't do that. But maybe ring? My int ring underscore? Whatever. I don't remember how to do this. S ring. Where does a ring come from? Data ring. Okay. How did we do this before? Derive. Oh, right. Okay. So we first need to derive instance new type. Derive instance new type my int underscore and then this. And derive new type Sorry, I don't do this very often, so I'm still a noob. Okay, so now we have a ring. We need to define G inverse prime. And then do we get negate? The derived new type instance does not include a derived superclass instance for semi-ring. Okay, that fixes the warning. All right, so that was kind of annoying, I guess, but I guess this works. It just requires this ring stuff, which I don't understand yet. But I know, like, I have heard before that integer is a ring, which is why I wasn't concerned about doing this. And I think this is just right. Kind of not what I was expecting, I guess. But I think it's right. And I guess it's the only way that you could do this is like you need to be able to go get the inverse, and that's the function that you're looking for. So then you'll take, like, given an A, so the property is inverse x like this, right? So you take the inverse, you combine it with its x, and then that better be equal to mempty. Then you could test that for all A. You need an eq instance, obviously. Interesting. Pretty cool. I've been trying to think about properties again, because I started doing some property stuff. All right. Anyway, pretty cool. It would have been nice if it was explained that the implementation for the like the sum, like one of these is, like what the implementation is, but doesn't matter. All right. So modular arithmetic and groups. Imagine you have a clock with 4 positions instead of 12. This clock starts with 0 instead of 1. Let's start at position 3 and add 3 by going clockwise 3 positions. So 1, 2, 3. So 3 plus 3 is 2. This kind of arithmetic is also known as modular arithmetic. So we start at 2 and add 3. Once again, we move clockwise 3 positions and wind up at 1. Okay. This clock represents the integers mod 4. Yep. Symbolically, it's displayed as D4. I don't know that this has like a specific name, but I know that you can do it with the Math BB library in LaTeX. I think that's what it's called anyway. It's been a while. Okay, so anyway, which is the following set 0, 1, 2, 3. Notice that these are the same numbers on our clock face. What about subtraction? We can by going counterclockwise, but since we're interested in modular arithmetic in the context of groups, and a group only has one binary operator, let's look at how we can get the same result as subtraction using addition instead. In math, we learned that subtracting is like adding the inverse of a negative number. Yep. Here, -3 is the inverse of 3. In modular arithmetic, we also have inverses, but they aren't negatives. Uh-huh. In regular arithmetic, this is just a and minus a. But this is not the case for modular arithmetic. Notice how subtracting 1 is the same as adding 3. This makes 3 the inverse of 1, vice versa. Three, the inverse of 1. Because we're trying to get to 0? Is that the idea? Yeah, because 0 would be the identity element. Yeah, that makes sense. Yep. Okay, so we've shown that integers mod 4 or z4 with a binary operator of plus meets the unique requirement for a group, but we need to make sure it's a monoid. Can you have something that's a group and not a monoid? I don't think you can. But anyway, we'll keep going. Yeah, it's like literally a sentence later. I always do that to myself. Yep. Um, Interesting. I never thought about modular arithmetic as like this, so this is kind of cool. So modulus forms a. Yep, that's correct. Yeah, but like the idea is like don't think about subtraction because we're trying to turn it into a group using the associative operator plus is the idea. But yeah, 100%. 100. Okay. So an abelian group. Yeah, it's pretty cool actually. I've not really thought about it this way before. And like you have this group property that I don't know that I've ever exploited. Um, like I've certainly used modulus before, but I've not thought about it as a group or really a semi group or a monoid. So kind of interesting. Okay, so abelian group. An abelian group is a group where the binary operator is also commutative. This is named after 19th century mathematicians Niels Henrik Abel. All right, so both plus and star are commutative. So the following groups are also abelian groups. Mm-hmm. Cool. Uh, Niels Heinrich Abel is Norwegian. Assume that's what you mean. I don't know much about uh famous mathematicians. Famous chemists, a little easier for me, but famous mathematicians is a little harder. All right, so in PureScript, Abelian group is just a type alias. So we have a group and we have a commutative um, type class. But I would guess commutative type class is also just a type alias. We can check. Um, Commutative. What what would it define? Oh, it doesn't define anything. Okay, that makes perfect sense. So it's a class, but it doesn't define any operators because it can't. Like all it defines is another property. Um so what about I'm wondering if abelian is actually not a type and it's a class. Oh, it's a type. Why is it not a class is the question. Probably just because commutative is a separate class already. I wonder what else commutative is used for. Anyway, we know that type aliases are nothing more than macros. Do we know that? I don't know if I've ever heard that said, but you can think of the right hand side as replacing everywhere the left hand side is used in your code. Yeah. Okay, so when I first saw this, I was confused until I realized how it's used, which made me realize that it's poorly named. That it's poorly named. Imagine we have the following type alias. Type constrain Abelian. Abelian AB is a much better name since it reminds us that Abelian type class gives us a way to easily constrain A to be an Abelian group. In other words, A must be a group and commutative. But what exactly is commutative? A commutative is a type class. Yep. In PureScript and Haskell, for that matter, you can enforce commutativity of an operator. So the best we can do is just define it as such. Yeah. So like, yeah, when you have these things in PureScript, you have to test them, or like you wouldn't just make something commutative if it wasn't. That wouldn't make any sense. It would be confusing as a user. To give it a feel for how this type class is used, let's look at this simple example. So find. Whoa. So the B in the alias definition is the function's full signature. In other words, set A to maybe A. This expands to group A, commutative A, set A, maybe A. This is strange. I'm a bit confused by this, honestly. Um, it's this arrow No, it's the other arrow. Okay. So I think the trick here is that you can't have like two super classes from different, like, I don't know what the right term is, like hierarchies. So it's like Abelian is part of this group hierarchy, but it's also part of this commutative hierarchy. And so you can't like describe that this way. Can I? Oh, this is different. Okay, so go. So this is fine. But what does this mean, I guess, is the real question. And why is it not like this? I'm gonna have to ask about that one because honestly, I'm like pretty confused. Um, so this is kind of interesting to me. I'm not really sure why you don't do it this way. It seems to me like this is like what you're trying to say is like a superclass of these two things combined or something. But again, I've not really used this at all, so like I don't really know what to do with it. Okay, anyway, arithmetic operators in pure script. Let's see if we can get how much more do we have? Oh, we have quite a bit more. But we probably can get rid of the arithmetic operators and we can do semi rings, rings, and Euclidean and other rings. All right, so if we look at plus, we'll see that it's a semi ring. The only part of that is baffling is this semi-ring constraint. The A to A to A makes sense. In fact, it implies that plus is closed for the set of inhabitants of type A. So semi-ring is at least a magma. Next, let's try to see what multiplications type signature is. It also has semi-ring. What about subtraction? This was unexpected. It has a ring constraint, whatever that is. And finally, division has a Euclidean ring. So we have semi-ring, ring, and Euclidean ring. Who would have thought that simple arithmetic operations that we learned in grade school would be so complicated? Turns out that in pure script, arithmetic operators are defined using these abstract algebraic structures. The benefits of doing this is that operators can be used for non-numeric things, giving us the full power of these abstractions. The benefit of doing this is that these operations can be used for non-numeric things, giving us the full power of these abstractions. Okay, so yeah, next time we'll start with semi-ring and go from there. I'm like this isn't exactly clear, like when things should be a semi-ring and that sort of thing. Excuse me. But it clearly defines the semantics of the plus operator, the minus, and then the multiplication and division. So we just need to figure out those things. All right, cool. So thanks for hanging out, everybody.